Just a valid relationship here to set up should you be asked to. Okay. Who has heard of an ideal dilute solution? Anybody? Okay. It is something that we made up to make calculations simpler, okay? So ideal dilute solutions simplify calculations of chemical potential. We know we're no longer talking about maybe ideal gases here, right? We're talking about molecules in solution, but some of those same assumptions are helpful for us to use. So one of the things that we're first going to start with, our first assumption, is that the solute does not interact with other solute, okay? So this is kind of similar to ideal gases when they hit each other. Either they don't hit each other, or when they do, there's like nothing happens. We just imagine it's perfectly beautiful and elastic. The solute does not interact with other solute, only with solvent. What is our solvent for all of this? It's water. And like I said, we'll go through this sort of in more detail on Wednesday. But we assume that our biochemical standard state water concentration is 55 molar. And the concentrations of the solutes we're working in are about on the order of millimolar. So we're so far away from it, the molecules can't even find each other. They only hit other water. They never hit each other. Okay. Assumption number 2, enthalpy is independent of concentration. And this is sort of goes with number 3, that any changes in chemical potential are due only to changes in entropy. This term here is the only thing that matters in looking at changes in chemical potential. I know that's not real. I told you earlier, like, oh, hey, maybe that one extra molecule that you put in has some difference in enthalpy to consider. Think about only entropy. We know putting in one more molecule changes entropy of the system, and for an ideal dilute system, we're only going to talk about entropy changes as the number of molecules change. Okay. And sort of our last piece here, with these assumptions, what we can write is that chemical potential mu is proportional, because we're not going to think about enthalpy changes, and they're not interacting with each other. We have so much water, we can just let chemical potential be proportional to the natural log of concentration C. Okay. I think this follows. I keep talking about the direction things would flow. We know that things are going to flow from high concentration to low concentration. Chemical potential, not surprisingly, is related to concentration difference. Okay. So then, what this mathematical relationship looks like is change in chemical potential would be equal to chemical potential at state 2 minus chemical potential at state 1. This would be equal to gas constant times the temperature I'm at times the natural log of C2 over C1. Okay. C1 and C2 are concentrations of molecules between two different states, between two sides of a membrane, between like before I went into the cell and after I went into the cell, whatever it might be. What's the unit for concentration we're going to use? Molar in moles per liter. Okay. We'll be in molar units. Okay. Capital M is how we'll see this written. The units of chemical potential are energy over either molecules or moles, depending on what I tell you we're in. Okay. And again, in here, we're comparing two solutions. We're comparing the inside, the outside, two different things, whatever it might be, two different time points, whatever happened. Okay. R is gas constant, which is Boltzmann times Avogadro's number. What is mu with a superscripted degree? What would I name this? Standard state chemical potential. I love it. Standard state chemical potential. Okay. How about this one? It's standard concentration. What do we think the standard concentration is? Slash, I already told you. It's 1 molar, okay? So if I want to compare anything to standard state, okay? So let's say I want to compare my state, my solution, my system, whatever I'm interested in. If I compare to standard state, then mu is equal to standard state, mu, plus RT, the natural log of concentration over standard state concentration. Okay. This whole piece here is unitless because it's canceling out. But we almost never write this bottom because we're just dividing by 1. Okay? So I think what you'll just start to see going forward is that if I want to calculate chemical potential of something, I can calculate it relative to standard state by looking at standard state chemical potential plus gas law times temperature times the natural log of the concentration I'm at. Okay? And I won't write the 1 on the bottom.